Okay. In section 2, we developed an analytic method for finding explicit solutions to separable differential equations. Many interesting problems were separable, but most aren't. The qualitative and numerical techniques from 1.3 to 1.6 apply to a much wider range of problems. It would be nice if we could extend our analytic methods by developing ways to find explicit solutions of equations that are not separable. Unfortunately, there's no general technique for computing explicit solutions that works for every differential equation. Although we know from the existence theorem that every reasonable differential equation has solutions, we have no guarantee that these solutions are made up of familiar functions such as polynomials, sine, cosine, x. In fact, they're usually not. Over the centuries, mathematicians have dealt with this dilemma by developing numerous specialized techniques for various types of differential equations. Today, these techniques are available in Mathematica. Nevertheless, you should be familiar with a few of the standard analytic techniques that apply to the most commonly encountered types of equations. In this section, we developed two of the standard techniques for solving the most important type of differential equation, the linear differential equation. Linear differential equations are of the form dy dt is equal to a of t y plus b of t. Okay, so here's a couple examples. T squared y plus cos t. A of t is t squared. B of t is cos t. Oh yeah, there you go. Here, this is an example of just one that's more complicated, but it's the same stuff. A of t times y plus b of t. And it's very similar to like y equals mx plus b. Sometimes it's necessary to factor. So here we can find that even though this one doesn't look linear, it actually turns out to be linear. Differential equations have a bunch of categories. So in this one, here's an example of an autonomous linear differential equation. Here's one that's not linear, y squared. And we could see if we did f of x is equal to x squared, and then we had the expression, a x plus by. We applied f to that, and we checked if it was equal to a times f of x plus b times f of y. We would get, on the left-hand side, ax plus by all squared. And we'll check if that equals a times x squared plus b times y squared. And no, it's not. So this is nonlinear. Okay, you can change the names, but as long as there's of that form, at, bt. Okay, this one is linear and separable. This one is separable but not linear. Okay, so those are good examples. All right, so now there's two more classes. Linear differential equations come in two flavors. If b of t is equal to 0 for all t, then the equation is said to be homogeneous or unforced. This is like very similar to linear algebra in like the ax equals b. If b is 0, then it's a homogeneous equation. Okay, otherwise it's non-homogeneous. Okay, example of homogeneous, example of a non-homogeneous. A first-order linear differential equation is a constant coefficient equation if a of t is a constant. Okay, so let's just write that down. So homogeneous if b of t is equal to 0. Non-homogeneous else. Then the last thing was constant coefficient is y dot equals lambda y plus b of t. Lambda is basically just a real number. Okay. The principles of linearity. Linear differential equations are important for many reasons. They're used to model a wide range of phenomena such as the decay of radioactive elements, the cooling of a cup of coffee, and the mixing of chemicals in a solution. In fact, when we start the modeling process, we almost always try a linear model first. Not only do we want to keep the model as simple as possible, but we want to exploit the fact that the solutions to a linear equation are all related in a simple way. Given one or two non-trivial solutions, we get the rest by the appropriate linearity principle. Okay, so in the homogeneous case, there are two linearity principles, one for homogeneous and one for non-homogeneous. We begin by the homogeneous case. If y h of t is a solution of a homogeneous linear equation, so y sub h of t is a solution of y dot is equal to a of t y. So this is linearity principle 1. Okay, then k of yh of t, then k times y sub h of t is also a solution Okay, so the theorem, we verify this theorem simply by checking that k times yh of t satisfies the differential equation. In other words, if y sub h of t is a solution, we get d kyh dt is equal to k times dy h dt, which is equal to k a of t yh. Okay, fine. The theorem's not very surprising because, all right, oh yeah. All right, so yeah, so just notice that it's separable. Separable. So dy dt is equal to a of t y is equal to integral of 1 dy over y is equal to the integral of a of t dt. Then we get basically ln of y plus c is equal to the integral of a of t dt. Then we get basically y is equal to k times e to the integral of a of t dt. And then that's this. Consider this. Okay, so we get an example. It's actually pretty cool that the solutions are constant multiples of each other. Yeah, I like this. This is very neat. Remember that the linearity principle only applies to homogeneous linear equations. For example, it's easy to check that y1 of t equal to 1 over t 1 minus t. The solution of a nonlinear equation. Hold on, let's do that. I'm so bad at that. So if we have 1 over 1 minus t is equal to y of t, we're going to get dy dt. Um, so let's how do you do this? What are the steps for this? Because I got it wrong. I got wait. 1 minus t minus 1 dt. Or okay. Oh yeah, they cancel out. Okay, that's fine. Okay, so we're gonna get 1 over 1 minus t all squared. Oh yeah, and then so wait, but then okay, all right, it works out. Yep, that's a solution. The non-homogeneous case, although the linearity principle does not hold for non-homogeneous linear equations, there's a nice relationship between its solutions and the solutions to its associated homogeneous equation. Okay. Consider y dot equals a of ty plus b of t. Okay, and it's associated homogeneous equation. If we have any solution of the homogeneous equation and any solution of the non-homogeneous equation, then the homogeneous plus the non-homogeneous is a solution of the non-homogeneous. Whoa, something smells like it's on fire, man. Okay. If KYH is the general solution of the homogeneous equation, then the first half of the extended linearity principle says that for any KYH plus YP is a solution of the non-homogeneous equation. The second half says that any solution YQ can be written as okay, wait, hold on. If YP is a general solution is equal to T over 5, then we're saying dy dt is equal to cos T times T over 5 plus 1/5 1 minus T cos T. So T over 5 is equal to, or not T over 5, 1/5 is equal to, so if we multiply by 5, we get 1 is equal to cos T times T plus 1 minus T cos T. Then these cancel, and then you get 1. Okay, fine. That's fine. The extended linearity, okay. Once we have a particular solution, the extended linearity principle tells us that the general solution, okay, so for this, then YH of T is, what is it? It's KE to the sine T. So the general Y of T is equal to KE to the sine T plus T over 5. Yeah. Wow, that's really weird, man. solving linear equations. We now have a 3-step procedure for solving linear equations. First, we find the general solution of the homogeneous equation, separating variables if necessary. Then we find a particular solution of the non-homogeneous equation. Finally, we obtain the general solution of the non-homogeneous equation by adding the general solution in the particular solution. In theory, we could solve any linear differential equation using this procedure. In practice, this technique is used only for special linear equations such as constant coefficient equations. The limitation is caused by the fact that the second step requires we produce a particular solution. If a of t is not a constant, this step can be really difficult. If a of t is constant, then we can sometimes use a time-honored mathematical technique, guessing. For example, consider the non-homogeneous linear equation minus 2y plus e to the t. The associated homogeneous equation would be minus 2y, and its general solution is ke to the minus 2t. The hardest part of guessing a solution to the non-homogeneous equation is deciding what to guess. This task is made easier if we rewrite the equation so that all the terms that involve y are on the left-hand side. In other words, we rewrite the equation. Okay, so let's just do this. Okay. How to guess. Okay, so y dot equals minus 2y plus e to the t. So the homo part of it is y dot equals minus 2y. So yh of t is equal to ke to the minus 2t. Now rewrite to y dot plus 2y is equal to e to the t. I don't know why. Now we need to guess a function y p of t such that if we insert y p of t into the left-hand side of the equation, out pops e of t on the right-hand side. Okay, perhaps we should let the differential equation tell us what the constant should be. Okay, method of undetermined coefficient. Wow, this is really weird. But okay, I guess I can accept it. In the previous example, we guessed one. Okay, next example. Whoa. That's crazy, man. That's really what you do? We could have predicted some of this behavior without computation. If we look at the slope field for this equation, we see that for y greater than a half, the slopes are negative, and for y less than 1/2, the slopes are positive. Graphs of solutions with initial conditions that are outside the interval eventually into the strip of the two determined by the. Consider which one? Y dot plus 2y is equal to 3e to the minus 2t. I got alpha equals 3, beta equals -1. Oh, they guessed this. I just put a parameter there. Wait, so what is my solution then? It's because then we get 3e to the minus t. All right, minus 3 to the e to the minus t plus 2 to plus 6 e to the minus t is equal to 3 e to the minus. Wait. I don't think I did it right. Oh, yeah, I definitely did this wrong. No. B has to be -2. Wait, but then that doesn't work out. What? Hold on. Let's start over. We write our question. I got that far. Then they guessed this, which is a pretty good guess. But you still end up with -2a e to the minus 2t plus 2. You get 0. No matter how we pick alpha, it's still going to get 0. None of the solutions in the non-homogeneous equation are of that form. We failed because our guess is bad. We failed because our guess is a solution of the associated homogeneous equation. What's up, Oviedo? Huh, that's pretty interesting. I didn't even realize that. Our guess must contain a factor of e to the minus 2 to have any solution hope of being a solution. That I kind of get because it's on the right-hand side. Right? We need a guess that contains e to the minus 2t, but is not a solution of the homogeneous equation. See, because this is what I picked. A e to the bt. We need a guess whose derivative has one term that is... Dude, I don't like this guessing nonsense. We need a guess whose derivative has one term that is just like itself and another term that involves e to the minus 2t. What? The product will suggest that we need to guess whose derivative has one term that is just like itself and another term that... Okay, I got that. I got this. I got this. A times 1 minus 2t e minus 2t. Substitution of the derivative we obtain. And we get... Okay, so we're going to get 8 minus 2t plus a e minus 2t 1 minus 2t. How do you simplify that? Oh, so like this cancels and this cancels and you're just left with a e minus 2t. Okay. Oh, wow. That was a long section, dude. What's up, Ninja? Yeah, I'm watching chat. I'm not watching it constantly, but I look at it. Okay, so you just gotta guess. Damn. All right. I mean, I guess practice is gonna make perfect when it comes to this thing, but I don't love it. Okay. Problem 1. Find the general solution. All right, since I set this up, let's do this thing. Wait, we want to get this like this. Okay, so the step one, find YH of t. So this is going to be this part. So dy dt is equal to minus 4y. So what we're going to do is then, I mean, this should just be YH of t is equal to e to the minus 4t. Right? But let's just double check. So we're going to get dy over y is equal to minus 4 dt. So we integrate and we get ln y is equal to minus 4t. Okay, there we go. That's enough for me. So now, so this is the solution. Well, I guess YH of t is equal to ke to the minus 4t is the general homogeneous solution. So now what we want to do is we want to figure out for dy dt plus 4y equal to 9e to the minus t. Oh, shit. Sorry about that. We need to... maybe I can do this. Okay. So we want... All right, so if we just start... We're going to start off with the easiest one. We're going to start off with... a e to the minus t is equal to y. Yp of t, is that what we're saying? So then what we're going to do is dyp dt is going to be equal to minus a e to the minus t. So then we're going to have minus a e to the minus t plus 4 times a e to the minus t is equal to 9e to the minus t. So then if we factor out, we're going to get e to the minus t, or a e to the minus 1 plus 4. Okay, so we should be able to just get 3a to the e to the minus t is equal to 9. So a is equal to 3. So then our particular solution is equal to 3e to the minus t. If we then, so then the general solution, y of t should be equal to, and we can verify that that's right. So this is going to be minus 3 plus 12 is 9. Okay, that's correct. So now the general solution is going to be minus 4 e to the minus 4t, right? Plus 3e to the minus t. Oh wait, but no, this is the general solution. So don't we have times k here? Let's see. Wait, so do I substitute it back in? No, it's not. You don't substitute it back in. You just add it. You just add it together. So it's going to be, so you can get rid of the 4. You can get rid of the -4. You can get rid of all that. It's just going to be, it's going to be y of t is equal to k e to the -4t plus 3e to the minus t. This is the general solution to the linear non-homogeneous equation. Okay, so the second one is y dot equals -4y plus 3e to the minus t. This one looks very similar. So first off, the homogeneous, so y h of t is going to be equal to isn't it just going to be k e to the -4t again? Because dy over y is equal to -4 dt. Yep, okay, so that's correct. So now we're going to guess yp of t is equal to a e to the minus t again. So we're going to get minus a e to the minus t plus a e to the minus t. Wait, I did something wrong. Because the what did they call it? The normal form? The general, what do they call it? The standard form. The standard form is dy dt plus 4y. So we actually want a 4 here. Is equal to 3e to the minus t. So in this case, we're going to get 3a e to the minus t, which is, so a equals 1 equals 3e to the minus t. So a equals 1. So I'm pretty sure that the general solution is going to be y of t is equal to k e to the minus 4t plus so the general solution is going to be e to the minus t. So it's just going to be plus e to the minus t. Um, So what did I get? I got c e to the minus 4t plus e to the minus t. All right, cool. For k and r. Okay, number 3. All right, these have gotten easier now that I'm doing these. But I also picked dy dt is equal to minus 3y plus 4 cos 2t. Okay. So in this problem, the first step is that we're going to find that yh of t is equal to e to the minus 3t. Ke to the minus 3t. So I think we're probably going to do the thing from the book that we get. So then we guess that yp of t is equal to hold on. What did they guess? They guessed a cos 2t plus b sine 2t. So then we're going to get 2a sine 2t minus 2b cos 2t. Is that right? Yeah. Okay, so that's all good. So the standard form is it's going to be 2a sine 2t minus 2b cos 2t plus 3 times a cos 2t plus b sine 2t. And this whole thing is going to be equal to 4 cos 2t. So then we're going to get a system of equations whereby so the coses need to stay, but the sines. So we have 2a plus 3b is equal to 0. And we have 3a minus 2b is equal to 4. So that linear equation is going to be 2, 3, 3 minus 2 is equal to 0, 4. That doesn't work. Hold on, let me just solve it on the computer. So we want to solve for 2, 3, 3, 2, backslash 0, 4. I got, what is it as a fraction? Can we do, is there a way to do rational dot this? Rational dot this. Okay, so I got A is equal to 12 over 5, and B is equal to minus 8 over 5. Yep, okay. So, all right, so that's that. So now we should be able to get the general solution, y of t is equal to k e to the minus 3t plus, this is going to be big, wait, hold on, I'm getting confused. When we do this, we guessed this, but we guessed this. So it's going to be that. So it's going to be A plus 12 over 5 cos 2t plus or minus 8 over 5 sine 2t. So this is the general solution, hopefully. I'm gonna double check it really quick, but I'm pretty sure that that's right. Wow, the trig ones are annoying just because the expressions get so big. Wait, 2b plus, what did I have? 2b, oh, wait. Wait, what did they have? Oh, they had A on the sine term. Should it be any different? Evidently it is different. Now let's try one more time then. I'll do it just one last time since I got it wrong. So we're going to have yp is equal to a. Oh, is it because the derivatives were wrong? Oh, yeah, I did the derivatives wrong. Yeah, because it's supposed to be minus 2a plus 2b. So then you end up getting... this is the derivative term. So this is going to be minus 2a plus 2b, and then this is all good. So then you're going to get minus 2a plus 3b and 2b plus 3b. Wait, that doesn't sound right. 2b plus 3a. Okay, so the equation is actually minus 2, 3, 3, 2. So if we change that linear solve call from, it's going to be okay, so yeah, so instead it is A is actually 12 over 13, and B is 8 over 13. And so this is a plus. Okay, there we go. Now we have the general... Now we have the general solution. Okay, we can move on finally. Number 4. So this one is dy dt is equal to 2y plus sine 2t. So again, we're going to have... This one's going to be a little interesting because it's going to be... the homogeneous solution is going to be equal to e to the 2t. Ke to the 2t for k and r. Now, we're going to guess that the particular solution is equal to a cos 2t plus b sine 2t. And so then we're going to get for dyp dt is equal to minus 2a sine 2t plus 2b sine 2t. So then we're going to get for the thing is minus 2a sine 2t. Yeah, you need complex numbers to solve that. I think it's, what is it, I? Yeah, it's I, Yash. Okay, so plus 2b sine 2t. Now we're going to get minus, and this is going to be minus 2 times yp of t. So this is going to be a cos 2t plus b sine 2t is going to be equal to sine of 2t. So now when we look at the coefficients, wait, why did I get sine and sine here? Wait, how is that possible? This is cos. This is cos. All right, so sine, cos, cos, sine. Okay. So now we're going to get minus 2a plus minus 2 times b is equal to 1. And that's because there's a 1 here. Then we're going to get 2b minus 2a is equal to 0. Okay, so our matrix for this linear system is going to be minus 2, minus 2, minus 2, 2. And then we're going to times x is equal to 1, 0. I don't know if that's right, but we're going to try it. So the linear solve is going to be minus 2, minus 2, minus 2, 2. And we're going to get 1, 0. Okay, and I got that A is equal to minus 1/4 and B is equal to minus 1/4. All right, so that means that our general solution y of t is going to be equal to k e to the 2t plus, well, I guess it's going to be, or minus 1/4 cos 2t plus sine 2t. Okay, I'm going to double check my answer, but I'm feeling pretty confident with these trig ones. These basic trig ones, I feel like I can do them. Here, let me get my chat up on my phone because the chat doesn't work here, man. Oh yes. All right, we got it right. This is right. So we're good. All right. I'm kind of enjoying these actually. Okay, so the next one is going to be number 5. And it's y dot equals 3y minus 4e to the 3t. What's up, Anu Bahab? Okay. All right, I got the chat up, so now I can read your chats. All right. So we're going to solve this one. So we're going to start out, the homogeneous solution is going to be equal to CE to the 3t. And we can see that just because this homogeneous, if we separated it out, this would be equal to CE to the 3t as its general solution. Now what we want to do is write this in standard form. dy dt minus 3y is equal to minus 4e to the 3t. So we're going to guess, and I'm pretty sure that our guess will work if we set our guess to yp of t is equal to ae to the 3t. So now what we're going to do is we're going to calculate dy p dt equal to 3a to the e to the 3t. So now we're going to get 3a e to the 3t minus 3 times a. Oh no. So that's not going to work. Okay, this is one of those ones where you can't, you have to use something besides the general homogeneous solution, because it's not going to work, and we're going to see that right now. So I'll just do it. So we can see immediately that these are going to cancel out, but this right hand side is equal to minus 4e to the 3t. So so this is no good. Get some water. Okay. Well, that's all right. So they suggested in the textbook that you just add a t. Okay, but if instead we guessed yp of t equal to at e to the 3t, then dyp dt is equal to ae to the 3t plus 3at e to the 3t. So then if we had and then this is going to be minus 3 times y, which is at e to the 3t. Oh, that's cool. Okay, I get it. So now we can get these to cancel out, but we get an extra guy. So see, these are still going to cancel no matter what a is. And this is equal to minus 4e to the 3t. So now we can just say a, that must be equal to minus 4. Okay, so then our general solution, y of t, is going to be equal to k, or it's whatever, c e to the 3t plus minus 4 t e to the 3t. So let's get rid of that. That. Okay. These tricks are really goofy, man. These tricks are really goofy. Generally, I'm like, I don't know. It's like, I don't know. It's just funny that we have to learn so many tricks. Tricks are for freaking kids, man. All right, so number 6. Number 6 is weird. We have y dot equals y over 2 plus 4 e to the t over 2. Okay, so we should get e to the 1/2. Oh, interesting. Okay. So we're going to get for the homogeneous, sorry, yh of t is equal to e to the 1/2 t. Or ce to the 1/2 t. Now, if we guess, so we're going to get y dot minus y over 2 is equal to 4e to the t over 2. If we guess for yp of t is equal to, again, ate to the t over 2, or not t over, yeah, t over 2, then dyp dt is equal to a e to the 1 t over 2 plus 1/2 ate to the t over 2. So now we're going to get y dot, which is ae to the t over 2 plus 1/2 ate to the t over 2 minus minus 1/2 ate to the t over 2. Again, we're going to get this cancellation. Then we just get a is equal to 4. Okay. So then we're going to get y of t is equal to ce to the t over 2 plus 4te to the t over 2. Right, I'm going to double check that one just to make sure that we got it right. Oh my gosh, there's 34 exercises in this section, dude, and we've only done 6. That's so weird, since the forcing matches the homogeneous root. They just seem so niche. Anyways, the solution is correct. Okay, so we got it. Um, all right. 2-minute break. 5-minute break. I don't know. Okay. Let's wrap this section up. So we need to do some more practice. So we have number 7, solve the initial value problem. So we have dy dt is equal to plus 2y is equal to et over 3. And we have the initial condition that y at 0 is equal to 1. So basically, when we solve this for the general solution, we get a family of functions. So we're going to just plug back in and find what we need. So the first thing we want to do is figure out this equation is the same as y dot is equal to minus 2y plus e to the t over 3. Now, our general solution, or homogeneous solution, yh of t is going to be equal to e c e to the minus 2t. Now, using this thing again, we're going to guess that yp of t is equal to a e to the t over 3. So then that means that dyp dt is equal to a over 3 e to the t over 3. So then we're going to get a over 3 e to the t over 3 plus a e to the t over 3 is equal to e to the t over 3. So that means that 4/3 a is equal to 1. So a is equal to 3/4. So that means that our general solution should be y of t is equal to, so this is going to be the general solution, ce to the minus 2t plus 3/4 e to the t over 3. Now, if we plug in 0 for t, we're going to get c times e to the 0, so that's c, plus 3/4 e to the 0, which is plus 3/4. And this is going to be equal to 1. So c is equal to 1/4. So the full solution of this thing is going to be y of t is equal to 1/4 e to the minus 2t plus 3/4 e to the t over 3. So that solves the initial value problem. Just going to double check, but I'm almost positive. Okay, wait, I did something wrong. Hold on. Oh, you know why? Because I forgot a 2 here. So there's a 2 there that I forgot. So that 2, we then get What's up? Okay, so now, hello. Okay, so we got a 2 there, so then that makes this 7. So then that makes this 3 over 7. So then here, this is a 7, this is a 7, and this is a 7. So then this should be 4/7. So this is going to be 3/7 and 4/7. Cool. Okay, that's correct. I just double checked. So we are now on to number 8. More solve IVP. It's not. It's not. I promise. It's really not. Okay. So number 8. Number 8 is dy dt is equal to 2y plus 3e to the minus 2t. And we have the initial condition y of 0 is equal to 10. Okay, so the way to solve this is, first off, we recognize it's linear and it has a constant coefficient in y. So we know that the general homogeneous solution, yh of t, is going to be equal to e to the 2t. ce to the 2t. We have a coefficient here. Then we're going to have y dot minus 2y is equal to 3e to the minus 2t. So now we make our guess for what yp of t is, and we're going to guess a e to the minus, to the minus 2t. So then that means that dyp, let's see, am I still in frame? Perfect. Dyp dt is going to be equal to minus 2a e to the minus 2t. So now to try to solve this, we want minus 2a e to the minus 2t minus 2 times a e to the minus 2t, and that is equal to 3e to the minus 2t. So now is that right? I think that's right. So we're going to get, this is all equal to minus 4a e to the minus 2t is equal to 3e to the minus 2t. So that means that minus 4a is equal to 3. So then a is equal to minus 3/4. Okay. So the next step is plugging that back in, and we're going to get y of t. The general solution is ce we want the homogeneous solution, which is this, ce to the 2t plus hold on, this is going to be minus 3/4 e to the minus 2t, but we haven't finished yet because we need to plug in 0. So we're going to get 10 from this initial condition is equal to c times 1, because e to the 0 is 1, minus 3/4 times 1, because this is also 1. So c is equal to 10 and 3/4. What's infinity over I times infinity. I don't know if you can just do algebra on infinities like that. I don't know if you can cancel infinity. Okay. I'm going to double check this answer and then we're going to move on. Whoa. Okay, wait. So then y of t is equal to 10 and 3/4 e to the minus 2t minus 3/4 e to the minus 2. All right, so we did get it right, actually. So this is the correct solution for the general. Okay, what's the next one? The next one is a cos one. I don't know if we want to keep doing these because I mean it's pretty similar. Like I feel like I get the idea. All right, maybe we'll just move on to 13. All right, let's do 13. Number 13. Consider y dot plus 2y is equal to cos 3t. I'm probably not in the frame. Okay, so part A says guess yp of t equal to a cos 3t. Is there an a that works? So so dyp dt is equal to minus 3a sine 3t. And yh of t is going to be equal to e to the minus 2t, ce to the minus 2t. The next step is we're going to substitute it in. So we're going to get minus 3a sine 3t plus 2a cos 3t is equal to cos 3t. So even though we could use like the identity that sine 3t is equal to cos 3t minus pi over 2, we still won't be able to add these two together. So there's no value. Well, actually, hold on. So if we have minus 3a times cos 3t minus pi over 2 plus 2a cos 3t is equal to cos 3t I'm not convinced that there isn't a value of a that doesn't solve this. Okay, so if you try solving for a, with like a computer algebra program, you get a goes to cos 3t over 2 cos 3t minus 3 sine 3t. But what we need is which is not a constant. Hello, what's going on, bro? So since a can't, there's no constant for a that solves this equation. That means that our guess of the particular solution of the non-homogeneous equation is wrong. So we need to go back and guess again. So that's the answer to part A, is that there is no value of alpha. Now B, the question B is, explain why a good guess for yp t is a cos 3t plus b sine 3t. And the reason, oh shoot. Wait, hold on.